And let's continue to discuss the variability, the internal variability of the ocean. Last lecture was largely devoted to El Nino Enso pattern. And as you may remember, this pattern was stronger and more evident in the equatorial Pacific, but the connection in terms of oceanographic implication was larger, and even more effective was the teleconnection with the weather condition of the surrounding countries, and even its effect has been detectable even at a longer distance, like in Northern Europe weather. This is what we saw it happen in the Pacific. But what about Indian Ocean? We know that the weather pattern here is dominated by the monsoon, but what happened in the ocean? We have some another mode of variability that is similar to the ENSO here, and the answer is yes. We do have the so-called Indian Ocean Dipole. Indian Ocean Dipole is an irregular oscillation of the sea surface temperature. This is, as you already learned, is the easiest way to detect changes in thermoline properties of the ocean, because a satellite can help provide a lot of information and nice images, especially in a tropical and equatorial region where the sky is green. We have a daily huge a deluge of images that provide a high resolution pattern detection of the temperature pattern in the surface ocean. And this is the case for the Indian Ocean. And there is a permanent gradient or permanent structure dominated by the meridional variation in temperature. Here we are looking at the anomalies. So the changes that are found according with the reference of with standard year or standard seasonal cycle. And we can have two extreme situations for Indian Ocean dipole. One is the positive phase, which is associated of warmer than average sea surface temperature in the left side, in the western side of the Indian Ocean, and a negative or anomaly, so sea surface temperature which is cooler than average in the eastern part, and the colder or the negative phase of Iod is the opposite. We have cooler sea surface temperature if compared with the average on the western side, and warmer temperature on the east side. This has, as you see, important implication not only on the circulation of the ocean, but also on the weather. And these changes in sea surface temperature, as we saw in in the ENSO, they have implication in convection and in rain. Changing, warming the surface layer means that you have more thermal energy in atmosphere, more convection, more rain. The cooling it has the opposite, and this is exactly what we find, what's been found for the western coast of Somalia and the eastern Australia. Probably Australia is all under the IOD influence. So there is also an intermediate phase, which is the neutral one, in which warmer the two water pools at eastern and western side of the basin are more or less in equilibrium, or are very similar to the standard one. So no anomalies has been found. But we are more interested in looking at the extreme because they do exert influence on circulation and on atmosphere. These events, or the IOD events, are irregular and cannot be interpreted as an oscillation, but a departure from equilibrium or quasi-equilibrium states, so to say. And they start usually around May or June, and they have the peak between August and October. Then when the monsoon arrives, they rapidly decay, and in the southern hemisphere around the end of the spring. So as an episodic period event that lasts about 6 months, much less than the ENSO phenomenon. Well, now we know that the IOD exists, then we try to understand the mechanism that sustain or way on the onset of the positive phase. You see here, you have the Indian Ocean, you have Australia on the right side, Africa on the left side of the plate, and you have the cooler than normal area in correspondence of Sumatra Java coast. This is the start of the whole process. When typically, as we have the El Nino event as an anomalous perturbation, atmospheric perturbation in the middle of the western side of the equatorial Pacific, here we have anomalous upwelling event along the Sumatra Java coast. The upwelling season is always present here, but the intensity can change. And when you have an anomalous upwelling event during May, June, which is the regular, you have and the thermocline is uplifted, and the cooler water is reaching the surface. So they can exchange the heat with atmosphere. It gets cooler and cooler. It creates a pressure gradient between the eastern part and the western part of the of the basin, and this gives way to a westward wind anomaly, getting stronger winds along the equator, and this creates drives stronger recycling is a Walker cell again here involved. So we have stronger trade winds and increased convection, more rain, and aloft we have the return wind in the opposite direction. This is the coupling between atmosphere and ocean is similar, and similar mediation of the anomaly through off-equatorial Rossby waves is also found as in ENSO. So again, the wind anomaly and the Ekman pumping or suction and generates off-equatorial Rossby waves that travel westward, and its effect, as in the Nino, the deepen the thermocline in the western side. In this case, you may remember the Nino as an effect on the thermocline depths at the eastern side, and this essentially create situation that is depicted in this small cartoon of the image. So the equatorial thermocline is displaced at east, is shallower, while we have a downwelling in the ocean in the western side, and an accumulation of warm water. Not only ST, but the old water is involved with that. And the interaction between atmosphere and ocean are mediated by Walker cell circulation and having a source of energy, the coal and water, warm water pool at the eastern and at the western side of the ocean. And this has this pattern in place in let's say few months after begins, quite faster compared to the Nino, because the distance are lower, and so everything goes fast. And how we go to the back in the negative phase. The decay of the Iod event is characterized by a slow eastward preparation warm anomaly along equator. So the warm anomaly is propagated eastward, and this essentially this movement of water masses from the western part to the eastern part has a net effect to deepen the thermocline depth. When this deepening reaches the eastern side, you have deepening of the equatorial thermocline that induce or reduce the upwelling and reduce the rate of cooling. And this obviously changed the condition in energy transfer in atmosphere. And at the end of the day, we have a positive SST anomaly that is formed on the east side, and this creates again a situation in which wind reacts to the anomaly of surface temperature, but essentially in the opposite condition compared to the previous one. So we have a reversal of the anomaly in the circulation, atmospheric circulation. This is essentially the two phases of the same phenomenon. We have two water masses that are getting alternatively colder and warmer, and atmosphere reacts to this kind of changes. The mechanism is of the energy transfer in the ocean is essentially connected to the Rossby waves in westward and vice versa. The water masses are moved toward the eastern side in order to, well, guarantee the flip-flop behavior. However, I must say this is not an oscillator in a strict term. It is a perturbation that goes one way or in the other one. Which are the impact of IOD. It's quite obvious thing that since the monsoon is a dominant seasonal cycle in the area, some interaction between IOD and the strength of monsoon seems to be quite obvious in some sense. And especially the effect of the monsoon on the Indian subcontinent has been found in at least in 3 cases, and in 1997, 98, in 2006, and 2019. This last case is the most well known, studied. There are more data, and it is a recent one. And in 2019, the seasonal rainfall due to the monsoon over India was 110% higher with respect to its long period average for the same period, same area. But with a prominent modulation in June, the rainfall was quite low, 67%, while the September one was quite excessive, more than 150% more than usually. So at least for this extreme event, this anomaly was also found in the other IOD event. Seems to be quite well solid and sound. Being a regional pattern, but to some extent this involves a very vast area. It's quite obvious that IOD interact with similar phenomena like ENSO in Pacific Ocean, and we see later that this explanation or this connection has been proposed to explain some pattern of the IOD event of 2019. How frequent IOD is to have a strong event? We are looking at the temperature gradient. We see in a while how this is calculated, and looking at these indexes that track the onset and the evolution of the IOD. Well, we can find 4, 5 positive, negative IOD events during each 30 year, and which is frequently, not as frequently as El Nino possibly, and where the frequency is comparable, while Remember, the Nio happens between 2 and 7 years. It has very irregular period of onset. And but the more striking difference is the length. Here is intra-seasonal, let's say, perturbation, and while El Nino generally is longer than 1 year. But there is a need to keep track of the evolution of the IOD by using some indexes. And here the dipole, the index used for the IOD is called the dipole mode index, or DMI, which is the time series calculated by the difference of the surface temperature anomaly in two regions of the tropical Indian Ocean. One is in correspondence of Sumatra, Java, Apulian region is the origin of the positive phase of IOD. And the other one is the western side of the equatorial Indian Ocean, where the accumulation of the warm water takes place, where the warmer surface temperature anomaly are expected. And average temperature calculated anomaly, average temperature anomaly calculated in the eastern and western part are used to calculate the index. And this is a plot of the recent year of Indian Ocean dipole. And the anomaly are quite, for a large part of the period, are below 1 degree Celsius. But here in 2019, the difference was more than 2 degrees at its peak. It was in October. So the IOD in 2019 was extremely strong. And how this events can be detected in surface temperature. We have, there's a recent paper on that, and in the plate, you have the 9 months of sea surface temperature anomaly from June to November. The temperature plotted here are the global one. We are focused in the Indian Ocean, especially in the equatorial tropical Indian Ocean. Look at the June condition. The scale is in degrees Celsius. The red mean higher than usual. Blue is cooler than usual. And in June, more or less, you don't have any negative anomaly or limited negative anomaly. The whole area is warmer than usual. In July, something begins to happen on the eastern part, stronger along Java, Sumatra, and the pattern in August and September was stronger and stronger, and you see that the anomaly slightly propagate westward, and this takes place very well in October and November, where in November have very nicely subdivision on the pattern, where stronger area, stronger blue area was on the eastern side of the tropical Indian Ocean, and while very well established warm pattern was rimmed the African coast. So this is see a regional pattern, but you may note that the whole Western Pacific was warmer than usual. And there are some suggestions that in the strengthening of IOD in 2090, the role of the anomalies, SST anomalies of the Pacific Ocean was not negligible. And this is to just to corroborate the statement that IOD is part of a larger global system and obviously interact with them. We talk about rain in India. What happened on the other side of the basin, the Australia. And Australia usually experienced less precipitation during the positive IOD. We saw that the stronger convection area was on the African coast. And looking at this map, we have the ranges of the rainfall in expressed in the deciles. Essentially, red means very, very low, the lowest on record in precipitation, while the blue is the highest on record. In between, we have intermediate value. The very first glance of this map means that everything, especially the southern part of Australia, was reddish. This means that large part of the country has experienced below the usual average rainfall. And in some areas, not only in the eastern part as expected, but also in the western part, that could be somehow expected, but in the eastern part, a record low rainfall. This can be seen as a textbook example of the signature of a positive IOD event in Australia. And that's okay. So far, so good. And we saw IOD, we saw ENSO. We have other mode of variability that are have longer scale, and the IOD and or the and ENSO as an interannual or prominent interannual variability scale. There are other, and both of them has a connection with atmosphere. So we do need to consider, especially to this scale, that sort of interaction between ocean and atmosphere is necessary to be considered in order to explain and to understand how the oceanography process takes place. And we saw here in this scale different shape around the name. So we recognize ENSO and IOD, and the green box means interannual scale mole, and they have a black box with the Atlantic multi-decadal oscillation or Pacific decadal oscillation that are longer scale, we move from interannual to decadal or longer time scale. And then we have two or three atmospheric modes that are coupled, and they have this mode of variability. They are somehow connected to them, which are the northern annular mode, the southern annular mode, that are extratropical zonal wind pattern of variability centered at 50, 60 degree and 30, 35 degree latitude. And they are encompass the whole globe, while Nio is an index that measures the difference or anomaly in pressure between Iceland and the Azores. We see when we explore this long-term mode of variability of the ocean, that especially Nio has largely to Nio is ascribed largely the variability of the North Atlantic, but we've seen not only, also the Mediterranean, for example, is respond to Nio long-term variability. What is important to mention that while the oceanographic mode, long-term mode variability, has a prominent energy in the signal on the long scale, the atmospheric mode variabilities has the whole spectrum in. So they have a high frequency, a daily frequency, monthly frequency, annual, and even long-term variability. So the two structure in the power spectrum are quite different. The other point to keep in mind is the fact that there are mode of variability, so they come from an EOF principal component analysis, and so they are structured that in our understanding have sort of they exhibit a recurrent, let's say, exhibit the current pattern, positive, negative, and so on, but they are not intended, or in general, are not intended to be oscillator. In the sense, an oscillator, a typical oscillator is a pendulum. It continues if the pendulum has no friction. It's an ideal machine in which continuously the potential energy is transferred in kinetic energy and again in potential energy. So one phase is the prerequisite for the successive one. The maximum energy, potential energy at the maximum height as the prerequisite in order to obtain maximum velocity at the lowest part of its path. So this is not the case. Sometimes authors propose that one phase is a prerequisite for the successive one, but the frequencies of the events are not so regular in order to guarantee that these effects are always the dominant one. And so the preconditioning depends on the previous state. but and also the length and the onset has an erratic component that surely um, cannot support the concept of oscillator. So oscillation is a natural mode of variability. Oscillator is something more deterministic. The stochastic component of the atmosphere, the ocean, is quite important. So we speak about mode of variability instead to speak about recurrent phenomenon, regularly recurrent phenomenon. We face now one of the most famous, well-studied mode of variability, decadal mode of variability. This is called the Atlantic multi-decadal oscillation, or Atlantic multi-decadal variability. There are two names for the same phenomenon. And this is the dominant mode of natural variability that occurs in North Atlantic with a period of 60 to 80 years. And when you do AOF analysis, you can have higher modes, but so they can explain less variance, and probably the large part of the signal is retained by the dominant mode, and so it's good to analyze this as the most informative one. And AMO is based upon the average anomaly of surface temperature, again, in the North Atlantic basin. And here we have a pattern that probably has not need no a lot of discussion to get the major signal. You see a very strong warm spot in the North Atlantic. This is called the positive phase of AMO, and is obtained by a long reanalysis on the surface temperature obtained by the Hadley Center in the period of 1870 to 113. This is the special mode, so it's the EOF, the first EOF of the analysis of this long-term sea surface temperature anomaly. Again, to sum up the evolution in time, we look at the principal component of this. And the first graph in the plate show in black the evolution in the yearly evolution of the this index calculated in terms of anomaly of the surface temperature calculated in an area between 0 and 65 north and 80 west, 0 east. So the whole Atlantic here. And in red and in blue, you have low pass series in order to filter out the interrandom variability. Look at the long-term trend. You have red means the positive phase, blue is the negative phase. And with time, you see that the blue getting lower and lower, and the red is seems to be dominant. And the first explanation for this is that progressively AMO is positive phase is getting the dominant one. But the explanation is different. If you look at the global SST, there is a constant tendency toward higher temperature. Global warming has a net effect on the sea surface temperature, long-term sea surface temperature. And the centennial signal is quite clear. The temperature now are higher than the past. So if we have, if you subtract this global trend that has nothing to do with the natural variability of the ocean. This is a forced variability due to greenhouse gases, for sure. And so the two signals in the data are entangled. To disentangle it is suggested to trend the AMO index with a global SST index in order to subtract the trend, leaving the natural variability as it is. And in this case, well, the AMO signal is the trended AMO signal show a more, let's see, more regular variation between positive and negative phase. AMO index is based on SST. You know, SST is a cheap way to detect variability in the ocean. And yet the AMO index provides a simple, concise way to detect multi-decadal climate variability in North Atlantic. And this is associated with important climatic impact. What is quite important is that since the indexes are features that are, could say, proposed in order to simplify the detection of the variability on large data set. But they are somehow arbitrary. The news is that the AMO pattern is robust across different data sets. There are some reconstruction of the past SST due by different institutes, and the AMO pattern is robust. It doesn't depend on which kind of data set has been chosen to do the analysis. This is a good point. There are some adverse issues. One is the fact that we are looking at variability of the order of 60, 80 years, but the instrumental SST data are short in length compared to the multi-decadal time scale of AMO. And as I told you, SST is only a surface layer, and it doesn't directly capture the aspect to AMO current related to subsurface temperature. And SST obviously does not reflect variation salinity, which especially in certain area, subpolar area or polar area, can play a major role in changing density. And we also we don't have any information in the ocean-driven turbulent heat fluxes. So SST is a proxy, but it doesn't capture the full complexity of the thermodynamic dynamics of an ocean. And quantifying the relative importance of large-scale ocean circulation, especially the meridian overturning in the Atlantic, versus external radiative forcing in causing the AMO is challenging. So we don't know if the changes in SST due to the changes in solar radiation balance, budget, or in advection of heat by circulation. And this is also a critical point to understand. So the final message, the take-home message is AMO index is good, is robust, but this is not the whole story. And just to show an example, and here you have the AMO index calculated on the Hadley cell in the area similar to the you can find here in the box, and the true line corresponds to two different areas of calculation. One smoother, and the green is the larger one, and there are some points marked by vertical red line in which changes of instrumental equipment used to detect is connected to the changes in the pattern here may be related to changes in instrumentation used for detecting or observing the SST. And this means that this could be a problem when you face long-term time series that for sure are not obtained using the same kind of equipment. And it's difficult to discriminate when where the changes are due to the sensor and the platform used for detecting the variable under observation and what is the natural variability. However, the long-term trend is still present, and also the prominent multi-indicator variability also emerge. Here you have a plot in which two different conditions are shown. One in red here is the period considered to characterize the maximum, the positive AMO index, and a subsequent one in which the AMO index conversely was at the minimum. And these are the variability that you can find in SST. In some part of the ocean, the temperature is 1 degree less. And this is quite interesting, because if you look at the rest of the ocean, the tendency is to have probably a little more warmer ocean, or neutral one. And the only cooling of SST is found in the North Atlantic. And this means that in some sense, North Atlantic has a peculiar behavior on this scale, which is not reflected to the global circulation or the global SST pattern. Before we go ahead and look at what are the motivation, which are the forcing that drive in this peculiar behavior of the North Atlantic. It's better to recall something that you have already heard. I'm sure that is North Atlantic oscillation, which is the natural mode of variability of the atmosphere in this area. And you have two phase as always, the positive one and a negative one. This is intimately connected to the fact that we have an index. The index has one way of changes to be positive or negative. You don't have any other possibility. So again, we have a positive phase, negative phase. But interestingly, the positive phase has is obviously calculated by this pressure gradient. Changing the pressure gradient, the storms that cross the Atlantic change the pattern and goes northward, where you have great wet condition, and little goes on the Mediterranean area that gets dry, and this high pressure also intensify trade winds and westerlies, while when you go in the negative phase, we have weaker and more zonal storm tracks that influence the Mediterranean area, while the Northern Europe gets drier. And these similar conditions are also found on the American coast. And opposite situation are in Greenland and the northern part of Canada. So the atmospheric circulation is weakened again. And so with a single index, we can more or less explain and summarize all these changes. This means that whenever you have a change in this pressure gradient, more or less the weather pattern and the climatic pattern are this way. And this is the strength of the Nio indexes. So there is strong correlation between this pressure gradient and the weather condition in this vast area of the northern hemisphere. The Nio index is named after Harlan, which proposed the calculation of this index based on the weather station measurement in Lisbon and in a station near Reykjavik in Iceland. And NIO, I mentioned NIO because NIO has been always proposed as the stronger correlation pattern with ocean variability. And we see here the observed AMO SST pattern. This is a structure that is calculated by regressing the trended North Atlantic annual mean SST anomaly on the observed AMO index for the period. And you have the AMO index, you have the correlation pattern of the AMO index with the with the spatial SST. So we see point by point how the AMO index, which is global one, is reflected in the area. So this is a quote unquote internal correlation pattern in which we can look at three major zones. One extremely positive, so the AMO index is strongly influenced by the northernmost part of the Atlantic. It's Labrador Sea, probably the Irmigan Basin. Then you have the mid-latitude, the Eastern Atlantic, which has also a positive part. And then you have a negative part, a negative area, which is along the American East Coast and the Caribbean island. So this tripole is quite a well-established pattern, SST pattern correlated with the AMO index. Again, this means how much the AMO index is playing the variability in this area. And that's good. If you look at the now SST pattern derived by regressing the tendon North Atlantic annual mean SST on inverted the trend Herald now index for this period, the same period, well, we obtain similar pattern. Here, on the western plate, we saw how the spatial pattern are related to the AMO index. Here you do the same for with the Nio Index. To make the thing simpler, we reverse the Nio Index in order to have a positive correlation. In practice, the correlation was opposite, was anti-correlated. But nevertheless, this trick makes the two images more simply comparable. And we see here, obviously, we have a different variable in place, and the pattern cannot be the same. The first one is the AMO, and this is now SST pattern. But again, we have a three-pole or three-band structure, which closely resemble, at least in space, the northern positive anomaly and the mid-latitude tropical anomaly that can be found or easily found also in AMO structure. While the negative anomaly that we have here, it's much, much stronger compared to that one found in the AMO SST correlation. So what we can say that? We can say that the variability in Nio explain a substantial, well, is strongly correlated to the variability obtained by in AMO index. So AMO index and NIO seems to be very well correlated in determining the spatial variability of SST in the Northern Atlantic over a very long, more than centennial time scale. The AMO tripole, is essentially the leading pattern on SST variability in North Atlantic, and is directly related to the ocean, of the ocean to the anomalous RC fluxes. And this is the deterministic or the dynamical explanation for that. So Nio as an index, but the changes in atmosphere weather pattern in storm tracks in the North Atlantic are physical processes that interact with the surface ocean. And these anomalies these anomalies can produce changes in RC fluxes and also in the SST property. There is an important issue. The two indexes are related, but there is a delay in the ocean system because the heat content of the upper ocean is much higher than in the water. The seawater is much higher than atmosphere. So changes in conditions in Nio condition or in the atmospheric condition in different Nio situation takes time in order to be captured and retained by SST. It takes about 1 month before the changed Nio signal is transferred to the ocean. And this pattern is has a lifetime which is about 1 year. So it's long and much more, much longer than expected from local damping to the RC interaction. And this is quite a peculiar phase. Why did this happen? There is an explanation. The formation of the upper seasonal thermocline in summer separate the upper layer from direct RC fluxes. And this reduces damping of SST anomalies, and this is the entrainment of the mixed layer the following winter. We saw this in the explanation of the mid-latitude reemergence of the anomalies in the upper ocean during the discussion of the mixed layer dynamics. And this is a typical case of the re-entrainment of mixed layer in the following winter. This is the memory of what happened some months earlier. And this also explains why the anomaly lasts so long. Very good. And we have here two slides, not very nice, but quite informative. In red, we have the power spectrum against frequency of the now Harrell index. And we have a IOF analysis of the sea level pressure, so in another atmospheric indicator. And the period is about 50 years from N7 car reanalysis. And you see that the energy in this curve for the Harrell is located in a lower frequency, and while the sea level pressure here is smoother and we don't have enough data for very low frequency. So the length of sea level pressure is lower and perfectly match the average of this decreasing pattern of the now Harrell index in expressing frequency. When you look at here, you have again a structure of SST expressing in its frequency domain. So we have a power spectrum of SST tripole, which has a similar long-term variability, and but there is a secondary power peak in the in the decadal scale at a slightly longer period than the Nio Index that has already this pattern, which is also present in sea level pressure. Here you have also two additional indexes calculated in the cross-equator SST difference and cross-Gulf string SST differences. This has been produced by Chaya and Marshall in the early 2000, and they found that again, both of them has a broad peak around at 10-20 years, with a marked reduction in power at low frequencies. So this the behavior of this gradient as a different behavior on long time scale, but confirm the presence of this decadal band. We are talking about the surface temperature, but as I told you since the beginning, that surely the ocean is intrinsically three-dimensional, and in this case, the subsurface condition plays a major role in determining the dynamics and of the variability, long-term variability of the space, and probably this is true in general. And since the last century, we start to collect direct subsurface ocean observation that give a better look on the long-term climate variability, and because the factor on a cycle or the month-to-month variability in the atmospheric circulation decay rapidly with that. So the memory, the very memory, is in the ocean interior, not in the surface. And we saw that as in the explanation for the tripole pattern duration, the importance of the memory of the system in the reemergent, captured by the reemergent process of the water masses formed with an anomalous characteristic of the water masses from the winter before. So again, the message is that the subsurface ocean is the real, or retains the real memory of the long-term variability. However, these long-term variabilities and the changes of the or the characteristics of the subsurface ocean are also ascribed to the to now, or to the changes in the weather pattern or climate pattern characterized by the now variability. There is a list of peculiarities of the ocean interiors that are related to the Nio Index. The temperature of the upper subtropical ocean has been linked to fluctuation to Nio Index, and Curry and McCartney discuss observed interannual to the interdecadal variability of the intensity of ocean gyres and related them to Nio forcing. The ocean gyres are a typical pattern as wind-driven. So also the inertia of the ocean gyre is large, but they are low pass filter, say, compared to the Nio forcing, which has almost a white noise spectrum. And so they has act as low pass filter of the signal of the forcing due to the atmospheric input. And another important issue for the meridional overturning and for the changes of the subsurface condition in North Atlantic is the ocean convection that takes place in Labrador Sea, Birmingham Basin, and this happened quite frequently, not all the year or not all the year in the same way, but the intensity of ocean convection has been observed to co-vary with the Nio, especially in the Labrador Sea. So we have a series of the dynamical and the processes that are related to the weather pattern and the climate pattern identified by the Nio index. And the explanation for the ocean convection as a dynamic explanation is the fact that the SST anomalies is propagating are linked to the property of water mixed at the end of the winter. Water formation means that you characterize the water formed in the period and changing the temperature also in surface, but in interior. And Labrador sea water, which is the end product of the transformation process that takes place during convection, exhibit extended warming and cooling trends consistent with the phase Nio. So if you change the Nio phase, you change the wind force, and this is important in the water formation. It's obvious that this signal is retained, and the retain is also in terms of properties. The denser they are, the deeper is the convection, and so this explanation seems to be quite consistent with the current theory of the dense water formation open ocean. Very nice. Everything seems on the same line, but very recently we, I found a paper. I'm not sure that this is really credible, but it's interesting to comment it, this man proposed that the periodicity of AMO in the last millennium was driven by volcanic eruption of other external forcing. And there's no compelling evidence for AMO being an oscillator of a cycle. So now can be the direct mechanism influencing the AMO, but the very forcing, or at least in this hypothesis, the very forcing is different. So the change in atmosphere depends on other external forcing that is mediated by the atmosphere and conveyed in AMO. So as we talk about oscillation, but it's not a cycle, it's not an oscillation, it has a response to an external forcing. This is more or less what I also told you at the beginning. So we don't have oscillator, we have oscillation. Here Mann suggested that even oscillation is not appropriate, but it's better to see is episodic events that trigger response by ocean via atmosphere changes. Which are the impacts of the multidecadal variability? And we have here the trend that the Nio Index from the observation. You have again in green the yearly variation, and then the smoothed one, which is the long-term multidecadal variation. And we can see that the AMO plays a major role in forcing the 20th century multidecadal variation of India and Sahel summer rainfall. You see, Sahel, well, has very nicely correlation with AMO just by looking at the two plots, see the negative and the positive phases quite well matched in the two cases. And India rainfall correlation is less striking, but still there are some the two plots show some similarities, especially for the negative part. And the AMO also is important to show to trigger the Atlantic hurricane activity, and the number of hurricane is also related to the well, quite well related to the AMO index, and this is quite obvious since is a local response of the atmosphere ocean system to the states, and this is locally related. The two other cases means that there are some teleconnections, atmospheric teleconnection that create this anomaly. And as we saw, the AMO has an impact in on atmospheric processes, on the weather in different region, and both in terms of hurricane or in rainfalls. And there is also a recent study that show that from the data, there is a change global scale multi-decadal variability of the sea surface temperature, which is when you detrend the sea surface temperature from the water or global warming effect, you have still a predominant global scale multi-decadal variability in place. And Young et al. Proposed that this global scale multi-decadal variability could be driven by not only directly a substantial part of the global ocean, but also through atmospheric teleconnection, atmospheric ocean coupling processes. Someone could say, since when you make an average of the global surface temperature, you include also North Atlantic. And North Atlantic has a prominent signal and variability. This influence GMV, but this is important. The relationship between AMO and GMV has a strong negative correlation, and means that the two are not in same polarity, but also there is a delay of 4 to 8 years. And this means that this cannot be a direct effect of average to two correlated data set, but is something more complex. The analysis of climate model simulation based on observed SST over AMO region shows that the atmospheric teleconnection between the tropical Atlantic and Pacific are the key factor linking AMO and GMV. So again, when you move to longer scale, you cannot disregard the effect of the atmosphere on the ocean and ocean on the atmosphere. This is true for local processes, but also at global scale. This is a nice example of what happened when you look at the SST signal and its variability, and you correlate it with a limited area, and the correlation is not due oceanographic processes, but to teleconnection, atmospheric teleconnection at global scale. And so far, so good for what regard the AMO changes. We have anomalous process that also took place in the 1968, that there was an anomaly that is not related to atmospheric processes, or not directly related to atmospheric processes, but had a quite important role in freshening different part of the North Atlantic. And this freshening event has been called or dubbed the Great Salinity anomaly, that took place in a subwater gyre starting in 1968. Most probably, the origin is not fully known, but observation suggests that it might have been generated by an unusually large Arctic Ocean ice discharge. And this is connected to atmospheric circulation and an extreme manifestation of quasi-decadal fluctuation. And this means that in the superposition of two concomitant forces in phase gives way to the melting of a lot of ice, Arctic Ocean ice, and this creates this great salinity anomaly that was being captured by the general circulation of the area, and was carried out slowly all around the Greenland coast. It took a couple of years to reach the Labrador Sea, and then was incorporated into the Gulf Stream that progressively reached Northern Europe, and a branch in went to the Azore here, and ending or in 8081, 8082, more or less in approximately in the same area where it has been generated. So it was a very nice advection process, experiment, natural experiment, to see how the large case simulation behaved here, and the salinity was, when separated by the surface, as a conservative property that can be tracked for many, many years. And so we see that the branches of this anomaly was found even in the North Sea, and also toward the Barents Sea, north the Norway. That's quite a nice event, which is happened once. Again, no periodicity for that, but still an interesting example of how changes in the large-scale pattern of circulation or thermoline property can be triggered by a single episodic event that influence an area for decades. I think that's okay for today. We'll stop here. And again, if you have a question, I'm here. And if you want to write me, it's good. I will send you a copy of the slides. And during the weekend, I'll send you my notes that are not cover fully the lecture. Most of the lecture are there. Parts are still in the slide. Please merge the two, and feel free to contact me at your convenience. So bye-bye, and see you, or remotely see you on Monday. Ciao, and enjoy your weekend. Bye-bye.
Bye. Thank you.
Bye.
Thank you. Have a good weekend.